Okay, to continue with our discussion of models, let's start by thinking about a population or a sample from a population of horseshoe crabs. We've weighed this population, so we have a long list of weights in grams, and what I've done here is display them in a histogram, which shows us the relative numbers of individuals in different bins. And this is a model of the weights of horseshoe crabs in our population. It's a particular representation of the real population of crabs. I could change my model by using different sizes of bins. If I use a smaller set of bin sizes, the total size on the side here goes down, but now I have many more bins, and it shows me a little bit more finely the resolution of what's going on. I could do other approximations. I could, for example, calculate different measures of the central tendency or of the spread of that data. All of those are approximations to the whole data set. In other words, they represent models of the data. There's another kind of model where I use a kernel density estimate to get a smooth approximation to the shape of that sample. But now let's think that we've got other things we've measured about our horseshoe crabs, including how wide their carapaces are. And we could do all the same things with horseshoe crab width. But in this case, and in many cases, we don't actually expect horseshoe crab width and horseshoe crab weight to be independent of one another. Bigger crabs are going to weigh more. So how do we approximate that relationship between weight and width? We've got sort of two different kinds of models that we can talk about. The first are what we could call functional or process models. These are models where you put in a particular input and you're going to get exactly the same output, or you get a particular output, unless it's a stochastic model, in which case you don't. Climate models are an example of this, population dynamics models. We have many, many functional or process models in science. Usually at some level mechanistic, in other words, they are attempting to represent the underlying mechanism by which a particular variable is changing through time or over space. Those are quite distinct from statistical models. In a statistical model, we recognize that the output is not exactly given by the input. They're often a little more phenomenological. In other words, we're trying to approximate the relationship between different kinds of variables, but we're not going to worry too much about whether the way we do that is directly related to the underlying mechanisms. The advantage that those two things give us is that we can then estimate the parameters of our model from observed data. Statistical models are pretty much what we're talking about everywhere in this course. So we can plot weight as a function of width for our horseshoe crabs, and unsurprisingly, bigger crabs weigh more. And we can calculate an approximation to that relationship using a straight line. This is sort of the most fundamental kind of two-variable statistical model that you could come up with. So the average weight is going to be equal to an intercept. That's where our y-intercept is way down where width is 0. Our crabs, we expect them to weigh minus 3,944 grams. And then for every millimeter of width, that weight increases by 242 grams. And then the important part here is we've got some error. The epsilon is the letter we give to sort of population error, but for any particular observation, we're going to have E sub I, which is going to be this red line here, represents the departure between our estimated mean and our observed data point. So the black line represents our estimated mean weight given a certain width, and then there's some degree of scatter around that line, or variation around that line between our observations. So this is what a bivariate regression model looks like. We've got our y, our dependent variable in some terminology, and I represents the index of each observation. There's going to be an intercept. What is the value of y, of the mean of yi when xi is 0, and then beta here is going to be the rate of increase in the mean value of yi for each unit change in x. So we've got two variables, y and x, and then we have epsilon, which is our error term, and that describes the scatter around our mean line. I'm just going to go over these assumptions briefly here. We'll come back to these in another video. We make a number of assumptions. First off, that the independent variables, that's the x, is measured without any error, and they're fixed, they don't change. The errors, those epsilons or e sub i's, those are independent. The value, knowing the value of one error for one observation doesn't tell you anything about the value of the next observation. We're also assuming that they're normally distributed and that they have constant variance, sigma squared. Finally, we're assuming the relationship between x and y bar, that is the mean of our dependent variable, is a linear relationship. And as I said before, this is probably the simplest assumption we can make, and it is one that is so useful in terms of describing the relationships between things that we're going to pretty much come back to it over and over again. One way that you could describe the content of the course of ecological statistics is what do we do when each of these assumptions are broken? Because typically in ecological data they're broken very regularly, and we still have to analyze data and make sense out of things.